Today we're going to talk about determinants and inverse matrices. Please make sure that you know what a matrix is, how to add, subtract, and multiply matrices before you watch this video. We're going to go back first to remind ourselves about what a mathematical identity is. The identity for addition means what can I add to something so that it won't change its identity or won't change the number. For addition, that number is 0, right? Because I can add 0 without changing a number's identity. The identity for multiplication, of course, is 1 because multiplying by 1 doesn't change a number. We're going to bring that into matrices now. So, what would be our additive identity matrix? If I want to add a matrix and have the result be the same as the original matrix, I have to add the 0 matrix. For multiplicative identity, or the identity for multiplying matrices, it looks a little different. It would have 1s on the diagonal and 0s everywhere else. This is actually called the identity matrix. It doesn't work for anything but just square matrices, but on any square matrix, a 2 by 2 or a 3 by 3 or bigger, it can even be an 8 by 8, it will still have 1s along that original diagonal and 0s everywhere else. So now we're going to talk about a matrix that will satisfy the following equation. So, if I want to multiply my original matrix to another matrix and come out with the identity matrix, this second matrix that I'm going to multiply by is going to be called the inverse matrix. So to start off with, I'm going to call this matrix A, B, C, D. Those are going to be my elements. If I multiply these two matrices together, if I do first row, first column, I'm going to get 3A plus 5C. And if you look over in the answer, first row, first column, it has to equal 1. If I do first row, second column, I'm going to get 3B plus 5D. And first row, second column, that needs to equal 0. If I do second row, first column, I get 7A plus 9C, and that has to equal 0. And second row, second column, 7B plus 9D. And if I look over here, second row, second column has to equal 1. If you look what we've got here, we've got two systems of equations in two variables. And I can actually solve these systems to find A, B, C, and D. And then I can put them in place to find my inverse matrix. We're going to go over how to do more systems with matrices tomorrow. For today, we're going to do it a little different way. We're going to use something called a determinant. Now, basically, a determinant can be found using the formula the first diagonal minus the second diagonal. When I talk about first diagonal, now I'm only using my original matrix. Okay? When I talk first diagonal, this is my first diagonal. Second diagonal goes from bottom left to top right. That's my second diagonal. If I multiply the numbers on my first diagonal, 2 times 8 gives me 16. If I multiply the numbers on my second diagonal, 6 times 4 gives me 24, and I'm going to subtract those two diagonals. First diagonal subtracting the second diagonal gives me -8. The determinant is -8. Now, when we use this in our matrices, we're going to say the determinant is 1 over -8 or -1/8. After I find the determinant, we're going to need to manipulate our original matrix. The first diagonal gets switched. In other words, the numbers are going to switch places. The second diagonal, the numbers are going to stay where they are, but both numbers are going to change sign. Then we're going to multiply our new matrix by the determinant. So, here's my original matrix. My first diagonal, instead of 2, 8, becomes 8, 2. My second diagonal, instead of 6 and 4, becomes negative 6 and negative 4. Then I'm going to multiply everything by that negative 1/8. Negative 8 over 8 is going to give me negative 1. 4 over 8 is going to give me 1/2. 6 over 8 reduces to 3/4, and the negative 2/8 gives me negative 1/4. This is our inverse matrix. If you go ahead and multiply these together, my original matrix with my inverse matrix, first row, first column, gives me negative 2 plus 3. That's going to give me 1. First row, second column is going to give me 1 plus a negative 1. That gives me 0. Second row, first column is going to give me negative 6 plus 6. That's going to give me 0. And second row, second column is going to give me 3 plus negative 2, which is going to be 1. This tells me, because that's the identity matrix, that tells me that this is really the inverse of my first matrix. Practice on these and come back and I'll tell you if you're right. Let's quickly look at the identity matrix of a 3 by 3. If I have a 3 by 3 matrix, remember the identity matrix, well, for multiplication, is I have 1s on the diagonal and 0s everywhere else. The determinant of a 3 by 3 is just a little different. I'm going to say that this is A, B, C, D, E, F, G, H, I. When I do the determinant of a 3 by 3, I'm going to start and use this very first column. I'm going to focus on the A, the D, and the G. I'm going to start with A. I want you to notice that if I took out the row and the column that A is in, I would have E, F, H, and I left over. If I took the determinant of E, F, H, I would get E times I minus H times F. Then I'm going to move on to D. I'm going to subtract D. Okay, notice how in the second one I'm subtracting. That's going to be kind of big. If I took out the row and the column that D is in, I'm left with B, C, H, and I. I want the determinant of B, C, H, and I. So I'm going to do BI, subtract HC. Then when I do this a third time, I'm going to add, so I'm alternating positive, negative, and positive. Okay, and then I'm going to move down to G. If I took out the column and row that G is in, I'm left with B, C, E, F. The determinant of B, C, E, F is BF, subtracting E, C. If I do this whole big calculation, that's going to give me the determinant of a 3 by 3 matrix. Write down any questions you have for me and we'll talk about it later. Your assignment is the Determinants and Inverse Matrices worksheet. Good luck!